Black holes stand as one of the most revered and destructive objects known to us in the universe, being notorious as all-consuming behemoths that swallow planets, stars, bend light and warp the fabric of space-time. Yet as destructive as they are, black holes harbour a mystery that has perplexed scientists for decades, and it is challenging our fundamental understanding of the universe. This mystery, known as the black hole information paradox, brings us to the edge of darkness, where the very nature of reality is questioned. To grasp its implications, we must first look at the origins of black holes and the principles that govern them. The first black hole was discovered in 1964. Called Cygnus X-1, located in the constellation Cygnus, it was initially detected as a powerful source of X-rays. The further observations revealed Cygnus X-1 to be part of a binary system where a massive unseen companion was pulling matter from a visible star, HDE 226868. As matter spiralled inwards, it was heated to extreme temperatures, emitting the intense X-rays we see, to reveal the black hole. This was an important discovery, as it provided the first compelling evidence that supported the existence of black holes. Up until then, they were a concept predicted by Einstein's theory of general relativity, which described how a massive object could warp the fabric of space-time, potentially leading to the formation of black holes. According to general relativity, black holes like Cygnus X-1 are the inevitable consequence of the collapse of massive stars that have exhausted their nuclear fuel. At the point of collapse, these stars succumb to their own immense gravitational pull, giving rise to regions of space where gravity is so intense, nothing, not even light, will escape. If any matter or information ventures beyond the point at which light is imprisoned, known as the event horizon, it will then be drawn towards the singularity at the black hole centre. Here, it is seemingly obliterated, leaving no traces of its existence in the observable universe. As the black hole continues to remove material from the observable universe, it will grow in size, and it will do so for as long as there is material for the black hole to consume. But imagine a universe trillions of years into the future, when it is in the twilight of its existence. The last vestiges of creation will have flickered out long ago, leaving nothing but all-consuming black holes, which in this distant future have nothing more left to consume. Doomed to roaming this empty universe, they will linger for eons, stretching beyond trillions of years, remaining dormant and unchanging behind the eternal prisons of their event horizons. But at this edge of darkness, something unexpected happens, with ramifications that shook the foundations of physics. In 1974, Stephen Hawking published a groundbreaking paper titled Black Hole Explosion. It turned our understanding of black holes on its head. Before then, black holes had been thought of as eternal prisons of consumed matter and energy, forever lost to the observable universe. But Hawking's brilliant mind introduced the concept of Hawking radiation, revealing black holes slowly lose mass and energy over time. He explains that at the black hole's event horizon, pairs of particles and antiparticles are constantly popping in and out of existence. Normally these paired particles would annihilate each other instantly, but occasionally one particle falls into the black hole while the other escapes its clutches. As the escaping particle leaves, it takes with it a bit of the black hole's mass and energy, suggesting that over eons of time, this process will cause the gradual evaporation and ultimate disappearance of the black hole. Like everything else in the universe, they have a life cycle. At first though, this might seem like a theoretical curiosity, but it opened Pandora's box as the ramifications challenge the very foundations of physics. On one side you have quantum mechanics that states as one of its principles, information about a system's initial state is never truly lost. a law that to quantum mechanics is sacrosanct. On the other side, if a black hole evaporates completely and the information about the matter it consumes is lost at the singularity, it violates the sacrosanct principle of quantum mechanics. This is the black hole information paradox, the crux of which lies in the concept of information and where it goes. Imagine on the pages of a book all the information that details a person's life, filled with stories, facts and data. But if the book is thrown into a black hole, classical general relativity suggests it is lost forever once it crosses the event horizon. The singularity at the black hole's core seemingly obliterating all the information contained on the pages of the book. But quantum mechanics, which governs the behaviour of particles at the smallest scales, tells us that the information contained on the pages can never truly be lost. This principle, known as unitarity, asserts that if you know the initial state of a system and the rules that govern its evolution, you can, in principle, reconstruct its past and predict its future. This means that even if the book is no longer accessible, the information it contained about the life story should still exist somewhere in the universe. Stephen Hawking's discovery of Hawking radiation has introduced a significant conundrum for physics. If information is truly lost in black holes, it would mean the fundamental breach of the principles of quantum mechanics. But if information is preserved, it challenges the current interpretations of general relativity, indicating that our grasp of gravity and space-time is lacking and needs revision. In pondering the black hole information paradox, we are drawn back to the awe-inspiring enigma that black holes represent. These beer moths, though among the most revered and destructive objects known, are challenging our deepest scientific understandings, and at the edge of darkness may ultimately reshape our understanding of the universe.